Welcome. Today, we're diving into the fascinating world of reinforcement learning, often abbreviated as RL. This field is a branch of artificial intelligence that teaches machines how to make decisions by interacting with their environment. Unlike traditional programming, where rules are explicitly coded, RL allows agents to learn from experience. Through trial and error, these agents gradually improve their performance at specific tasks. In this video, we'll break down the core concepts, explore real-world examples, and see why RL is such a powerful tool in modern AI. Let's begin our journey into how machines can learn to act intelligently. Reinforcement learning is a type of machine learning where an agent learns to make decisions by performing actions and receiving feedback from its environment. The feedback comes in the form of rewards or penalties, guiding the agent toward better choices over time. Unlike supervised learning, where the correct answers are provided, RL relies on the agent discovering the best actions through exploration. This makes RL particularly suited for situations where the optimal solution isn't known in advance. The agent's goal is to maximize its total reward learning strategies that lead to long-term success. To understand how RL works, let's look at its main components. First, there's the agent, which is the learner or decision-maker. Next, the environment is everything the agent interacts with. The agent takes actions, which affect the environment, and in return, the environment provides feedback in the form of rewards or penalties. This cycle continues, allowing the agent to learn which actions yield the best outcomes. States represent the current situation the agent is in, and policies are the strategies the agent uses to decide what action to take in each state. At the heart of reinforcement learning is a continuous loop. The agent observes its current state, selects an action based on its policy, and receives feedback from the environment. This feedback, in the form of rewards or penalties, helps the agent update its policy to make better decisions in the future. Over many iterations, the agent learns to maximize its total reward. This loop of observation, action, and feedback is what enables RL agents to improve their performance over time, even in complex and changing environments. The agent and environment are central to reinforcement learning. The agent is the entity making decisions, while the environment is everything the agent interacts with. For example, in a video game, the agent could be the player, and the environment is the game world. The agent's actions influence the environment, and the environment responds with new situations and rewards. This dynamic relationship is what drives the learning process, allowing the agent to adapt and improve over time. In RL, the state represents the current situation the agent finds itself in. Actions are the choices the agent can make in that state. For instance, in a chess game, the state is the arrangement of pieces on the board, and actions are the possible moves. The agent must learn which actions to take in each state to achieve the best results. By exploring different actions and observing their outcomes, the agent gradually discovers effective strategies. Rewards and penalties are the feedback signals that guide the agent's learning. When the agent takes an action, the environment responds with a reward, positive feedback, or a penalty, negative feedback. The agent's goal is to maximize the total reward it receives over time. This encourages the agent to find actions that lead to long-term success, rather than just immediate gains. The design of the reward system is crucial, as it shapes the agent's behavior. A policy in reinforcement learning is a strategy that the agent uses to decide which action to take in each state. Policies can be simple rules or complex functions learned from experience. The quality of the policy determines how well the agent performs. As the agent interacts with the environment and receives feedback, it updates its policy to improve future decisions. Finding the optimal policy is the main challenge in RL. Value functions are a key concept in RL. They estimate how good it is for the agent to be in a particular state or to perform a certain action in a state. By learning value functions, the agent can predict the long-term rewards of different choices, not just immediate outcomes. This helps the agent plan ahead and make smarter decisions, especially in complex environments where the consequences of actions may not be immediately clear. One of the biggest challenges in RL is balancing exploration and exploitation. Exploration means trying new actions to discover their effects, while exploitation means using known actions that yield high rewards. If the agent only exploits, it might miss out on better strategies. If it only explores, it may never settle on a good policy. Successful RL agents find a balance, gradually shifting from exploration to exploitation as they learn more about the environment. Reinforcement learning is all about learning from experience. The agent collects data by interacting with the environment, then uses this data to improve its policy. Over time, the agent builds up knowledge about which actions work best in different situations. This process is similar to how humans and animals learn through trial and error, gradually refining their behavior based on outcomes. It's important to distinguish RL from supervised learning. In supervised learning, the model is trained on labeled data, with the correct answers provided for each example. In RL, there are no explicit correct answers. The agent must discover the best actions through interaction and feedback. This makes RL more flexible, but also more challenging, as the agent must deal with uncertainty and delayed rewards. Unsupervised learning is another branch of machine learning, where the model tries to find patterns in data without any labels. RL is different because it focuses on learning to make decisions that maximize rewards. While unsupervised learning is about discovering structure, RL is about learning to act. Both have their uses, but RL is uniquely suited for tasks where decision-making and feedback are central. Many RL problems are modeled as Markov Decision Processes, or MDPs. An MDP provides a mathematical framework for modeling decision-making, where outcomes are partly random and partly under the agent's control. It consists of states, actions, rewards, and transition probabilities. By using MDPs, researchers can analyze and design RL algorithms more effectively, ensuring that agents learn optimal strategies. Policies in RL can be deterministic or stochastic. A deterministic policy always chooses the same action in a given state, while a stochastic policy assigns probabilities to different actions. Stochastic policies are useful in environments with uncertainty or when exploration is important. The choice between deterministic and stochastic policies depends on the problem and the desired behavior of the agent. RL algorithms can be divided into model-free and model-based approaches. Model-free methods learn directly from experience without building a model of the environment. Model-based methods, on the other hand, try to learn a model of how the environment works, then use this model to plan actions. Model-based RL can be more efficient, but also more complex. The choice depends on the task and available resources. There are many algorithms used in RL, each with its strengths and weaknesses. Some of the most popular include Q-learning, SARSA, and policy gradient methods. Q-learning is a value-based method that learns the value of actions in each state. Policy gradient methods directly optimize the policy. Each algorithm has its own approach to balancing exploration and exploitation, and to updating the agent's knowledge. Q-learning is one of the most widely used RL algorithms. It learns a value function called the Q function, which estimates the expected reward of taking a certain action in a given state. The agent updates its Q values based on the rewards it receives, gradually improving its policy. Q-learning is model-free and can handle environments with unknown dynamics, making it a versatile choice for many RL problems. Policy gradient methods are another important class of RL algorithms. Instead of learning value functions, they directly optimize the policy by adjusting its parameters to maximize expected rewards. These methods are especially useful for problems with large or continuous action spaces, where value-based methods may struggle. Policy gradient algorithms form the foundation for many advanced RL techniques used in robotics and game playing. Deep reinforcement learning combines RL with deep neural networks. This allows agents to handle complex environments with high-dimensional inputs, like images or sensor data. Deep RL has achieved impressive results in areas such as playing video games, controlling robots, and even beating human champions in board games. The use of deep learning enables RL agents to learn directly from raw data, opening up new possibilities for AI. Reinforcement learning is widely used in robotics, where agents must learn to control physical systems. Robots use RL to learn tasks like walking, grasping objects, or navigating environments. By learning from trial and error, robots can adapt to new situations and improve their performance over time. RL enables robots to operate in dynamic and unpredictable environments, making them more flexible and capable. Gaming is another area where RL shines. Agents can learn to play video games by interacting with the game environment, receiving rewards for achieving goals. RL has been used to train agents that surpass human performance in games like chess, Go, and various video games. The ability to learn complex strategies through experience makes RL a powerful tool for developing intelligent game-playing agents. Recommendation systems, like those used by streaming services or online stores, can benefit from RL. By treating recommendations as actions and user feedback as rewards, RL agents can learn to suggest content that maximizes user satisfaction. This approach allows recommendation systems to adapt to changing user preferences and provide more personalized experiences over time. In finance, RL is used to optimize trading strategies, manage portfolios, and make investment decisions. Agents learn to maximize returns by exploring different actions and adapting to market changes. RL's ability to handle uncertainty and learn from feedback makes it well-suited for the fast-paced world of finance, where conditions can change rapidly. Healthcare is another promising area for RL. Agents can learn to recommend treatments, schedule appointments, or optimize resource allocation in hospitals. By learning from patient data and feedback, RL systems can help improve outcomes and efficiency in healthcare settings. The potential for RL to assist in personalized medicine and decision support is immense. Despite its potential, RL faces several challenges. Learning can be slow, especially in complex environments with sparse rewards. Designing effective reward systems is tricky, as poorly designed rewards can lead to unintended behaviors. RL agents may also struggle with generalization, finding it hard to adapt to new situations. Researchers are actively working on solutions to these challenges, making RL more robust and efficient. Sample efficiency refers to how quickly an RL agent can learn from limited data. In many real-world applications, collecting data is expensive or time-consuming. Improving sample efficiency is a major research goal, with techniques like experience replay and transfer learning helping agents make better use of available data. Reward shaping is the process of designing reward signals to guide the agent toward desired behaviors. By providing intermediate rewards for progress, rather than just final outcomes, agents can learn more efficiently. However, reward shaping must be done carefully to avoid encouraging unintended actions. It's a delicate balance that requires domain knowledge and experimentation. Generalization is the ability of an RL agent to perform well in new, unseen situations. This is a major challenge, as agents often overfit to the environments they were trained in. Techniques like domain randomization and meta-learning are being developed to help agents generalize better, making them more useful in real-world applications. Safety is a critical concern in RL, especially when agents operate in the real world. Agents must avoid dangerous actions and respect constraints. Safe RL involves designing algorithms that prioritize safety, using techniques like reward constraints, risk-sensitive learning, and human oversight. Ensuring safety is essential for deploying RL in sensitive domains like healthcare and autonomous vehicles. Multi-agent reinforcement learning involves multiple agents interacting in a shared environment. Agents may cooperate, compete, or both, leading to complex dynamics. Multi-agent RL is used in applications like autonomous vehicles, resource management, and game theory. It introduces new challenges, such as coordination and communication between agents. Hierarchical reinforcement learning breaks down complex tasks into simpler subtasks. Agents learn to solve each subtask, then combine them to achieve the overall goal. This approach makes learning more manageable and efficient, especially in environments with long-term dependencies. Hierarchical RL is inspired by how humans tackle complex problems by dividing them into steps. Transfer learning allows RL agents to apply knowledge gained in one task to new, related tasks. This can speed up learning and improve performance in unfamiliar environments. Transfer learning is especially valuable when data is scarce or expensive to collect. By leveraging prior experience, agents become more adaptable and efficient. Imitation learning is a technique where agents learn by observing expert demonstrations. Instead of learning solely from trial and error, agents mimic the actions of skilled performers. This can accelerate learning and help agents acquire complex behaviors more quickly. Imitation learning is often used in robotics and autonomous driving. Inverse reinforcement learning is about inferring the reward function by observing the behavior of an expert. Instead of specifying rewards directly, the agent tries to figure out what the expert is optimizing for. This approach is useful when it's hard to design a reward function, but examples of good behavior are available. Autonomous vehicles use RL to learn how to navigate roads, avoid obstacles, and make driving decisions. By interacting with simulated or real environments, vehicles can improve their driving policies over time. RL helps autonomous vehicles adapt to new situations, handle uncertainty, and operate safely in complex traffic scenarios. Natural language processing, or NLP, benefits from RL in tasks like dialogue systems, text generation, and translation. RL agents learn to generate responses or translations that maximize user satisfaction or task success. By receiving feedback from users or automated metrics, NLP systems can continually improve their performance. Smart grids use RL to optimize energy distribution, manage demand, and integrate renewable sources. Agents learn to balance supply and demand, reduce costs, and improve reliability. RL enables smart grids to adapt to changing conditions and make efficient use of resources, supporting the transition to sustainable energy systems. Industrial automation benefits from RL in areas like process control, maintenance scheduling, and quality assurance. Agents learn to optimize production lines, reduce downtime, and improve efficiency. RL's ability to adapt to changing conditions makes it valuable for modern manufacturing and industrial systems. Resource management, such as allocating bandwidth in networks or scheduling jobs in data centers, can be improved with RL. Agents learn to allocate resources efficiently, balancing competing demands and optimizing performance. RL's flexibility allows it to handle complex, dynamic environments where traditional rules may fall short. Personalized education platforms use RL to adapt learning materials and strategies to individual students. By treating each lesson as an action and student performance as feedback, RL agents can tailor instruction to maximize learning outcomes. This approach helps students learn more effectively and keeps them engaged. Marketing strategies can be optimized using RL. Agents learn to select the best advertisements, offers, or messages for different customers, maximizing engagement and sales. By continuously learning from customer responses, RL-driven marketing adapts to changing trends and preferences, delivering more effective campaigns. The future of reinforcement learning is bright. As algorithms become more efficient and robust, RL will find even more applications across industries. Advances in deep learning, transfer learning, and safety will make RL agents smarter and more reliable. The potential for RL to transform how machines learn and make decisions is immense, paving the way for more intelligent and autonomous systems. Let's recap what we've learned about reinforcement learning. RL is a powerful approach to teaching machines how to make decisions through trial and error. It involves agents, environments, actions, rewards, and policies. RL is used in robotics, gaming, finance, healthcare, and many other fields. While challenges remain, ongoing research is making RL more practical and effective. Understanding RL opens up exciting possibilities for the future of AI. Thank you for joining us on this exploration of reinforcement learning. As we've seen, RL is a dynamic and evolving field with the power to revolutionize how machines learn and interact with the world. Whether in robotics, gaming, or healthcare, RL is shaping the future of artificial intelligence. Stay curious and keep learning. There's always more to discover in the world of AI.